So let's get started with the presentation. So as I have said that today's topic is Strut-and-Tie Method, STM, in reinforced concrete design. Let's go on to the next slide. These are the learnings and takeaways after the end of this presentations. So when I finish this, I will be like, let me put the laser here. So, okay. So when I will finish this presentation, these are the topics which are being covered. Like first, we will cover Bernoulli's theory, deep beams, what is strut-and-tie method. Then we will learn component of STM, nodal concepts, nodal strength check. Then we will see the design steps and STM modeling. And we will learn about effectiveness of STM and some applications and use cases. We will also see some limitations or drawbacks of STM. And at the end, I will do a small live modeling in SAP so that it will give a good idea about how we join the members and how we apply the loads and how we can get the output results. Okay. So moving on to the next slide, a brief introduction that conventional beam theory fails in D regions. D regions basically they are like discontinuity and disturbed regions, as it assumes the stresses is linear, which only happens in B regions, which is known as Bernoulli's or beam regions. So this is the like a primary, you can say a primary thing which is led to do STM in RCC beams or like other structural components, because the stress linear like the stresses are not linear in the discontinuity or disturbed region. It is only linear in B regions. So STMs provide a unified design approach in which a conceptual framework used to analyze and design reinforced concrete components where stress is found non-linear, as I've said. And this is the image where you can see this is the white portion, like which is B region. Here the stresses almost like they are straight line, but the gray area like this D region, you can see the stresses are non-linear. So we cannot simply apply our basic flexor formula here. We have to do something else, for which we do this STM. This STM is suitable for deep beams, corbels, pile caps, pier caps, and slabs and walls with openings. So let's study the Bernoulli theory, what it states. It states that plane sections before bending remain plane after bending. This is very normal and like basic thing that we learn in our like college days also. So like what it implies that stress in concrete or steel can be calculated using flexor formula, which is sigma is equal to my upon I, where m is bending moment, y is the distance from neutral axis, and I is the moment of inertia. This is a sketch which shows that we will assume that this stresses, the beam sections are straight, like they remain plane even after bending, and not like this, not like in slanted way or not like this in curved way. So it may happen in actual real life, but in our assumption, we assume that this will remain plane. So this is only valid for the B regions. So beam-like regions with gradual changes in geometry loads, not valid in D regions because stress distribution is non-linear there, which is shown in the previous slide as well. So let's go and understand the basic difference between deep beams and ordinary beams now. So parallel comparison is shown here that in deep beams, plane sections before bending does not remain plane after bending, which is a prime factor here, like why this needs some extra effort from our side to do STM. Whereas in ordinary beams, as I've said, plane sections before bending remains plane after bending. The resulting strain is not linear in deep beams. The resulting strain is linear in ordinary beams. Shear deformation becomes significant compared to pure flexor, whereas in ordinary beams, shear deformation is neglected. And in deep beams, it is subjected to two-dimensional stresses of flow, but where in ordinary beams, we have only one-dimensional stress of flow. These are some information about behavior, stress distribution, and strength, shear strength about the deep beams. So the behavior of deep beams is significantly different from that of beams of more normal proportions, which because that it requires special consideration in analysis, design, and detailing of reinforcement. The stresses distribution in the section of deep beam is nonlinear. This nonlinear thing is being pointed out again and again because this is very important thing. The linear elastic theory for the general beam analysis cannot be applied again. And the shear strength, because of their proportions, deep beams are likely to have strength controlled by shear rather than flexure. Because we do not apply the flexure formula, which is only applied in B regions. So in D regions, the governing things are like from shear. It depends on various parameters like compressive strength of concrete, shear reinforcement, and shear span to depth ratio, etc. Now coming on to the next slide, which is like the basic and very first definition of what is STM, like what it is meant. Why do we do this? So STM stands for Strut-and-Tie Method, basically a procedure used in the regions of concentrated forces and geometric discontinuities to determine concrete proportions and reinforcement quantities and patterns based on the analytic model consisting of compression struts in the concrete and tensile ties in the reinforcement. I'm gonna repeat this line. Please listen carefully. Like this is very important line. Patterns based on analytic model consisting of compression struts in the concrete. We will have compression struts, which represents the concrete, and we will have tensile ties, which represent the reinforcement, and the geometry of nodes where the point of intersection is there. This STM approach evolves as one of the most useful design methods for shear critical structures and for other disturbed region in concrete structures. We will learn about this more in our upcoming slides. The model provides a rational approach by representing a complex structural member with an appropriate simplified truss model. Truss model, I mean to say, like we have a structural member, a structural pier cap or pile cap we have, and then we will have a truss model based on it, which is hidden in that component. And we will see some images, then you will understand better. So, and the fourth is this point is also interesting. There is no single or unique STM for most design situations encountered. There are, however, some techniques and rules which help designer to develop an appropriate models. So there is no hard and fast rule that, okay, this is the only solution we got. There can be multiple solutions if we do STM for design purpose. Here are some examples, some snips, so that you can understand how the STM looks. So this first image is an image of bent cap. Here you can see like we have three piers on which they are acting as supports. From top we have girders, as it is mentioned, girder load, these red arrows, and here we have our truss. So these red members, you see, they are representing the ties, and ties we are meant for reinforcement. In the previous slides, I have stressed on that. And these diagonal members are strut, and these are meant for compression, which shows the concrete property, concrete capacities. And this is a bent cap, so like it's like basic thing, like in the bottom we will have tension, and on the top we will have compression. So this is the figure is also showing the same. In the second image, you can see like a basic RC beam is there, and the top, the real truss is there, which is being hidden in here. So we will analyze and apply forces on the truss, but in real world, it is hidden in the RC member, and where we will see how the members behave, how the forces are like coming in the components of the truss. The third case is an example of hammerhead pier cap. So here in hammerhead, as we were aware that hammerheads are like kind of like if we cut a section here, it will behave as a cantilever beam. And in cantilever beam, the things are other way around. On top, we will absorb the tension, and in bottom we will observe the compression. So as you can see, the green members here, they are representing the struts, mean the compression means the concrete. The top members are red members are ties, means the tension, which represents the steel. And fourth is an example of like corbel or a small cantilever beam. Here also the dashed are represented as strut. The solid line is tie. So I hope like the basic members, strut and tie, the tension and compression, the hidden thing, the truss, a basic understanding has been cleared with these images. Now let's go move on to the next slide. Yeah, so now we will go to the components of STM, like what are the things which is in STM. First thing is like strut. Again, a compression member represent basically concrete. Diagonal struts are generally oriented parallel to the expected axis of cracking. They serve as the compression cord of the truss mechanism which resists moment. They serve as the diagonal strut which transfers shear to the support. And there are some examples of how struts can be, like we can have a prism strut, we can have a fan shaped strut, we can have a bottle shaped strut. The commonly used is like prism, a normal struts where like the support and the reactions are like similar way. We can have these also in different scenarios. Next component is ties, which is tension member, represent basically reinforcement and steel. Tension ties include stirrups, transverse members, tension cord longitudinal members, reinforcement, and any special detail of reinforcement. It does not have anything to do with concrete. These are just meant for one part. It has only one job, which is to tell us how much reinforcement you are going to need in your member, in your structure. Second is the surrounding concrete is not considered to resist axial force in the model, as I have said. It has a critical consideration in the detailing of STM, that is the provision of adequate anchorage of the reinforcement. It helps us to give us the anchorage part also in the STM and in the structural member. These are some examples. Here you can see like this, the solid line is shown by ties. It is a deep beam example. Here it is a post tension member. The top member is tie. And as I mentioned, in cantilever hammerhead, the behavior is other way around. The top are tension ties, the bottoms are struts. Coming to the third component, which is nodes. These are connections on joints where like basically it represents the equilibrium. Okay, we have struts, we have ties, but what about that? Those points where they meet, where they finally join. So we have like classified in three groups, like nodes. We will study about these in upcoming slides as well. Nodes are analogous to joint in a truss, where forces are transferred between strut and ties. As a joint, like we will have a transfer mechanism on the joints, and we will have an equilibrium as well. They are subjected to a multi-directional state of stress. They are classified by the types of forces being connected at one point. So as in this snap, you can see like we will have a CCC node, which is like if all the compression members are meeting at one point. And we have second is CCT node, in which like two C are there. So two compression members are meeting at one point, but we will have a one tension member. So one T is there. And the third one is CTT node. So here we have one compression member, but we have two perpendicular tension members. So this is classified as the third one. And these the bottoms images are showing you the how nodal shape is will be there if we have the compression CCC, CCT, and CTT nodes. These values are signifying the efficiency factors, which I will let you know in the upcoming slides. These are also play a very important role. These 0.85 minus F dash C by 20 KSI, these factors, these efficiency factors are also very important. So onto the coming slides, there are nodal concepts. So we will understand and learn about what is this concept. So nodal zone, it is the volume of concrete that is assumed to transfer strut and tie forces through the node. Nodes can be proportioned in two ways. Like we will have two kinds of nodes. One is hydrostatic, another is non-hydrostatic. They are in coming to the hydrostatic, they are proportioned in a manner that causes stresses applied on each faces are equal. And in non-hydrostatic, they are proportioned based on the origin of the applied forces. So as you can see on the left side, hydrostatic, we will have a equivalent size of nodes where like we assume that the stresses on applied on the each face of nodes are equal. But on the non-hydrostatic, we will be having different kind of shapes at the nodes because it will depend on the origin of the applied force. Some face may be big, some face may be small. So non-hydrostatic nodes allows the geometry of the nodes to closely correspond to actual stress concentration because it gives the real idea. In contrast, the use of hydrostatic nodes can sometimes result in unrealistic nodal geometry because the assumption it is based on, it's simple that all the stresses are equal. Even it is not equal, we assume it is equal. So it gives the unrealistic nodal geometries and impractical reinforcement layouts. Hence, non-hydrostatic nodes are preferred in design and they are the mostly used in present days. So we will be using only non-hydrostatic nodes. Coming on to the more nodal concepts. So as I've said, we will learn about the efficiency factors. So first thing like CCC, here only struts intersect. Second one is CCT, nodes where tie intersect the node only in one direction. And third one is CTT, here the nodes where ties intersecting from different directions and one compression is there, C. So these are the more clear images in which more things are mentioned, like we have a bearing phase, we have back phase, we have strut to node interface. So these three phases are common in all the three kinds of nodes. And we have some different ideologies based on these phases as per the nodal formation. In this simple image, the third one, you can see the faces, like this is kind of back face. This is the top one is the bearing face. It is commonly where the girder loads are there. And this is the interface where we commonly have a strut. This interface connects with a bottom member. The bearing face, this is the face where like if we have a pier, we will have a support here. So the vertical to upward reaction will be coming. And this back face will represents the tie, the bottom member here. So this is the kind of configuration. As you can see, the first one is CCC and the second one is shown as CCT. So this is how internally in a structure member, the nodes and the connecting members are connected and are being shown. Like this is how it's behaved internally. The four tables is the table which is showing us the efficiency factors for nodes with crack control reinforcement. We will learn about crack control reinforcement as well. So these are those factors which I was showing like 0.85, 0.7, these things. So as per these values, we will do the calculations while doing the nodal checking. Coming to the next part, which is crack control reinforcement. So this is the reinforcement which is being like primarily intended to control the width of cracks and to ensure a minimum ductility for members so that if required, significant redistribution of internal stresses is possible. This behavior is consistent with the plasticity basis of STM. So here we have two formulas. This is based on AASHTO. The reinforcement in the vertical direction shall satisfy the following formula, which is AV upon VW into SV greater than equal to 0.0003. The same formula, but the difference is like we will have spacing as underscript as subscript as H, horizontal. The reinforcement in the horizontal direction shall satisfy the following formula, where AB is the total area of vertical crack control reinforcement with spacing SV. VW is the width of members web, and SV, SH are spacing of vertical and horizontal crack control reinforcement, respectively inch square. All areas are inch square, and AH is like total area of horizontal crack control reinforcement within spacing. And this is a snap where you can see that like these crack control are basically the phase bar. We commonly say the phase rebar, the stirrups, or you can say the horizontal bars, other than the top main longitudinal and bottom main longitudinal bars. So these we provide just in case to control the width of cracks in our structural members. And this is the basic formula we use to calculate this. Coming on to the, yes, there is one more important point that if we are not like sometimes we don't use this rebar in our calculations. So if we are not showing the crack control reinforcement, then we should use efficiency factor of 0.45 as the least value. We will not use the given values as per the formula in as mentioned in the table. Let me just go back. Yeah, here I can see this table. So here it has a range of 0.45 to 0.65. So if we are, this is just for the case if we are having crack control. But if we are not having crack control, then we will use 0.45 only in all the cases, which is being said here. So coming on to the next slide.
Look, just can you go back one?
Yes.
So let's say we use the 0.45 efficiency factor, right?
Yeah.
So we will avoid using any crack control reinforcement throughout the beam, but we would still require the face rebars. Is that correct?
Yeah, we will require phase rebars, but we will like we don't use these formulas specifically. We will use normal AST calculation for those rebars because these meant for specifically for crack control. Those will be just satisfying our minimum reinforcement criteria or shrinkage criteria.
So we will just put up the shrinkage rebar based on
Y-
AASHTO or whatever, just on the faces, and we won't put up the like the horizontal and vertical stirrups throughout the beam then.
Yeah, yeah. We will still have phase rebars, but the
Mhm.
yeah, the application point of view will change.
Okay.
We will provide in the sense of shrinkage or minimum reinforcement parameter. Then we will not mention the crack control thing.
Mhm.
Okay, yeah. So moving on to the next slide. So here we will have the nodal strength check. These are three basic steps which we will do on each node point where having a joint. So the first thing like the bearing phase, here we simply equate phi mv fc a bearing where phi is the resistance factor, m is the concrete confinement factor which I will discuss later. V is already discussed, which is efficiency factor. FC, we all know the compressive concrete strength, and A bearing is the area of bearing face. So, which we will equate it to compressive force acting onto the bearing face of that node. Here, like if node is failing or like if something unusual or unexpected is coming, like with the DCs. So here we have option to increase the bearing sizes for top member nodes, and we can imply that we can increase some column sizes for bottom nodes also if they are failing. Although this is very rare case, but yeah, we have an option to do this. Then comes onto the back face. Here back face we have some tensile ties also. So we have a reinforcement part as well. So as you can see in the from the above formula, this extra factor is coming here 0.8 into AST FY. So we equate this to compressive force similarly like above. Here we have an option to include the contribution of reinforcement as well if in case the node is failing. First, like we assume that okay, what about if we take only the concrete strength part? We will not take the reinforcement part. If it is passing, then it is more good. But sometimes the only like the concrete only concrete is not enough to pass the node. So we will then take the contribution from steel as well. So just along this point, you can see this image. So here, like the basic things, like here, if you see the force, just assume like this is the 1095 around kips is the force, and without rebar if I calculate it, my capacity is 811, my demand is this, my capacity is this. So it is not good, right? My node will fail. So is the contribution from rebar required? So this is showing yes. Then we will have a contribution from rebar also. We will change the formula and we will take this AST area of steel also, which is coming onto that node. And then we will see that our capacity has increased to this, and a demand is less than this, and we have a DC also, which is coming in good zone. So this is why this point is important, like how and when we take the help of reinforcement. The third is strut to node interface.
Just
Here,
something on that. Is it important that it needs to be CCT node for us to include the rebar or CCC? Also, we can just do. In your example, you have CCC only.
yeah, in example, I have CCC. So in this CCC, like we have a back face. So that back face, the compression is coming, but we will include the reinforcement as well, which we are providing on the top member.
Also, irrespective of it being all like struts onto the three faces, we can include the rebar capacity if you want.
Yeah, like this CCC is based on the behavior of the member which is coming onto that joint. Like the all the compressions are there. So we will have, okay,
Yes.
this is a CCC. But at that node, we will have like we will definitely have a top main rebar and bottom main rebar, either case.
Mhm.
So we will take the help of rebar which is already been there.
Okay.
Yeah, so this is also a good point. Thank you for pointing out. So third is strut to node interface. Here we will simply equate the equation like phi mv FCA strut to compressive force. Here we have also an option to increase the bearing sizes for top member nodes, and we will increase the column sizes for bottom nodes if they are failing. And this is a simple check, as you can see. I have not taken any this since this is strut to node interface, so in like almost 99% cases we will have a strut only, so we will not include any kind of uh, any kind of steel reinforcement part. We will do only on the basis of concrete. Coming to the next slide. Yeah, this is the confinement factor M value which I have been talking in the previous one. So this is where the supporting surface is wider than the loaded area on all sides. The modification factor M may be determined as you can see in the image, the loaded area is this, but when we see this section elevation view, our the supporting surface, that loaded area can be, sorry, the supporting surface can be greater than the loaded area. So it is expanded in the ratio of 2 horizontal, 1 vertical, and it can give us a A2 area, which is greater than A2, A1 area. So where the loaded area is subjected to uniformly distributed bearing stress, we will do this M A2 upon A1. A2 is greater than A1, obviously. A2 is the expanded area, and it should be less than 2. Second is the when the loaded area is subjected to non-uniformly distributed bearing stress. Sometimes it happens like bearings are tilted, or like it is not completely placed on the zone where it is should be. Uh, partial placement is there due to some skewness in the girders and all. So those rare cases are also been there. So in that cases, we use this kind of formula. And this is like M is the confinement factor, modification factor. A2, we call it as notional area, and A1 is the simple area under the bearing device. This is one factor that we also use. Coming on to the next slide is the design steps and its concept. These are like directly taken from AASHTO. Simple basic steps are there. I will show you like the basic steps in STM may be taken as first we determine the locations of B and D regions. Then we define the load case. Third step, we analyze structural components. Then we size the structural component using the shear serviceability check. We develop a strut and tie model. We proportion the ties, then we perform the nodal strength check, which been discussed very just now in the previous slide. Those nodal strength check we do. Then we proportion the crack control reinforcement as well if needed, and we provide the necessary anchorage for ties as well. And these are the design concept which we have to keep in mind while doing all these steps. Like equilibrium must be maintained. Second is the ties yield before struts crush for ductility. So this is also very important thing. We always want our ties or steel yield before struts. Struts represents here concrete, ties represents here reinforcement. If in case our concrete crushes first before yielding of steel, then our structure is not good. It is not optimized one, and we will not be having ductility. So it is a bad thing. So this is something which should be happen. Tension in concrete is neglected. Forces in thrust and ties are uniaxial. The angle between, yeah, this is also most important point. The angle between axis of a strut and tie should be greater than 25 degrees. The shear span to depth ratio A by D should be less than or equal to 2. So this is the basic parameter for dividing the D region and B region. If it is greater than 2, then we say that it is a B region, Bernoulli region. But if it is less than 2 or like coming like this, so we say that it can be a D region. External forces applied at nodes only. Pre-stressing is treated as a load. If we have a pre-stressing in our component, then we take that pre-stressing force as a load. And developing STM is an iterative graphical procedure. Like just doing one time, you cannot have a proper result. You have to do it multiple times, like multiple revisions should be there to have a proper optimized result at the end. So it is an iterative graphical procedure. Here, these are some modeling, STM modeling steps. This is also mentioned in AASHTO as per clause 5.8.22. So at the interface of B region and the D region, we have to ensure the internal forces and moments within the B regions are applied correctly to the D region. A tie must be located at the centroid of reinforcement that carries the tensile force. We should minimize the number of vertical ties between a load and a support using the least number of truss panels possible, while satisfying the 25-degree angle rule. We have to keep this in mind as well, that we have to keep 25-degree angle also greater than this, as shown in the given below figure. The strut-and-tie model must be in external and internal equilibrium, ensure proper reinforcement detailing. So these are some methods for formulating STM model. We can have elastic analysis based on stress trajectories. We can have simple load path approach, like we will see where the loads are going and like how it will go. And as per that, we will put struts and ties there. We can have a standard model also. Sometimes we just have standard basic models and we will just use it for our structure. In this image, if you see, like if you focus it, you can see the left side, it is being shown efficient. And on the right side, it is being shown inefficient. The reason for inefficiency is like, first thing, it is having multiple vertical ties, which should not be there. Like as per AASHTO, we should minimize the vertical members. And the angle, if we measure this angle might be less than 25-degree as well. So this is inefficient. On the other hand, we have only one vertical tie and the angles are also good. So this is efficient. That's the basic difference. I have an example also for this while I will represent in SAP. So that way you can understand that this thing in a better way. Then we have the effectiveness of STM. An efficient STM accurately mimics the actual internal flow of forces, the load path within a concrete member after it cracks. So there are some characteristics of efficient models. This aligns with elastic theory. Struts and ties are oriented close to the direction of principal compressive and tensile stresses. This maintains safe angles. The angle between strut and tie is kept within a safe range. This is the safe range. Simple and direct. It uses the fewest number of members. As I mentioned, we should use minimal number of members necessarily to stably transfer the load from the point of application to the support. And what impacts it gives on the final results. So predictable performance. The structure will behave exactly as intended under service loads with minimal unexpected cracking. Ductility. By placing steel ties exactly where the tension is, the structure can yield safely and predictably before failure. So this is something which we want. Like we want our steel to yield first before the concrete trusses. Before the strut failure, we will want that steel should yield. So this is good thing, ductility. Third one is material efficiency. Overall reinforcement is optimized. One of the most good like advantage, the reinforcement we get from STM analysis is optimized, meaning you don't waste steel where it is not needed. We only provide steel wherever it is needed. Coming on to the next slide, here we will have some like poor model and good model, like how we should keep an approach while modeling it. There are some tabular way, a table in which like parallel comparison has been done. Example of good and poor STM. So this good STM, it follows natural elastic flow of forces and load path. In poor STM, loads are assumed to pass through high indirect artificial zigzag paths because that's why this is poor. Well proportioned angle typically ranges between 25-degree to 65-degree. This is a example of good STM. In poor STM, too shallow, we can have less than 25-degree rule, or we can have overly steep truss, which is not so good. Minimal control cracking structures perform well in day-to-day use, whereas in poor STM, extensive wide cracking angle, large deflection as the structure forces itself into unnatural path. The steel ties yield safely and predictably before any concrete fails. This is coming again, this point. The concrete node crush or split prematurely due to extreme localized stress concentration. As I've said, like if our concrete node crushes first, then this is a sign of poor STM. Our structure is not good. The last stage, steel is placed exactly where the tension naturally occurs, minimizing waste and congestion. And in whereas in poor STM, it creates heavily congested steel layout. The amount of steel is also more that make pouring concrete difficult, because while pouring, we should have ensure a proper spacing between the rebar so that the aggregates, concrete slurry, and all those material can go into the member, and we can have a good finish of a concrete also. So this is also one point. If we put poor STM, we can have a highly congested rebar layout in our structure, and this is uneconomical as well. Coming on to some limitations. Yes, so many discussions have been done for advantages and all those things. Now we will learn some, like we will see some limitations. So the basic advantage can sometimes turn into a drawback, which is there is no unique solution. Different designers can model completely distinct truss paths for the same geometry. Finding optimal paths that closely aligns with natural elastic fields depends heavily on engineering judgment. So this is something which like if 4 to 5 people are working on a same model, same structure, they can have different STM as well. Not all are correct, but few are more efficient, few are poor. So this is sometimes a kind of disadvantage also for STM. Sometimes simplifying complex 3D stress flows into 2D plane truss is highly challenging. Calculating exact nodal geometry or which type of node formation would occur if multiple struts or ties meet at nodal zone creates uncertainties. So you will not find case where only CCC or CCT nodes are coming. You can have multiple struts or ties meeting there. So there you will have to like pass your judgment and do the equilibrium thing and maintain the nodal zone correctly as per the requirement, because you will get confused there what my final node will look like. Is it be CCC or is it be CCT, because multiple ties of struts will be there, so we will get difficult, like it will create some uncertainties. And fourth one is like satisfying local peering or nodal stress capacity is often mathematically tedious and it is highly conservative. Conclusion. Okay, so these are some findings, advantages, like some like what we concluded from this PPT and what we like learned. So for deep structures such as pile caps, STM more closely addresses the reality. STM allows flexibility in arriving at solutions. Typically, STM results in higher flexure reinforcement, but you don't have to check shear. Understanding the STM helps distribute reinforcement appropriately. The STM formulations that require the least volume of steel will be the solution that best model the behavior of a concrete member. This approach holds great promise for the DOTs and design offices, which could develop or obtain standard STMs for certain commonly encountered situations. So a good benefit, like if we have common encountered situations like common bend caps or common hammerhead pier caps, we can have one model simply and we can use it again and again for future purpose. So this is good. Standard reinforcement details based on STM could be developed for common situations. The STM then could be reviewed and revised if their parameters change. Obviously, if some design parameters or geometry or some point of load application changes, we can do some basic changes in the STM as per the parameters change. And in reality, there is almost an art to the appropriate use of this technique. Like it is something like not totally engineering basis. It is something like which is related to art also. Like it is on us, it is on the person, it is on the engineer, how he will model the truss, how he will show the forces and reactions and all. So this is like with time one can develop a good art in it. So at the end, I will just show you in 5 minutes, like I will show you live walkthrough of an example of a pier cap STM modeling, and we will see the output results as well. And these are some general requirements before start making the STM. So we will need overall geometry of pier cap, dimensions, bearing location, column sizes, etc. We will need loads as per required load combinations. We need bearing and pedestal sizes, and we need one software also to see the result output like SAP2000 and LARSA. The one I'm using currently is SAP2000. Let me just switch to the software to show you a live modeling. So this is SAP is open, and so here we will have one vertical tie. I will join this and this. No, sorry. We can have a member from here to here. And our truss is completed. So there are 4 girders points, this G2, G3, and G4. We have 2 supports, this support, left support and right support. And this is a vertical tie. With this help, we can see the vertical tie force and we will provide the stirrups and all. So this is our first preliminary steps. Let's model this same in the SAP. So the grid lines and all the basic distances are predefined here. Like if we go to edit data, so here I have like pre-entered these values. These values we can get from the geometry of the pier cap, like from where the G1 and the supports are, like how much far they are kept. This is in feet, and the height of the STM is also mentioned here, which can be calculated easily. So, okay, let's just model it. So I will just take a member and I will join this member here. Then I will join this member to G2, then to center, then to G3, then to G4, then to right support. From here to here, I will have one number, and from here to here, I will have number. From here, I will connect it. Okay, next step is having a vertical member here. And I will connect this to this. Let me see once again my STM. Okay, this looks good. And this member will connect to this. This member will be connected to here and here. So our basic primary STM modeling is done. Yeah, this looks similar. Okay, now we will make supports. So we will assign the support here. We will have a pinned support here. And here we will have a roller. Okay. Then we will provide the loads. So look for the load parts, like I have one report open from which like I will see the loads. These are the loads, bearing 1, bearing 2. These loads we can get from we receive from either from clients, or we can also develop the loads at our end. So these are the strength load that I will apply on the top of the truss. Let's just apply it. Okay. So this is the position of G1. Here I will apply the loads. Forces. I will go to the strength 5 load pattern, and in this here I will apply loads 9.7 4. The negative sign I am putting because it will be a downward force. First force is applied on G2. I will apply next force. Click on apply. On G3, I will apply one more force, which is 572.65. Click on apply. And on G4, I will apply one more force, which is 5,778. Okay. All the strength loads are being applied. Now I will apply the dead load, which will be applied on each of the nodes. These points where I'm applying the dead loads, these are called nodes here, because here these members connect. So assign joint load forces. I will keep the load pattern as dead load, dead weight, dead load, and here I will apply the force is 56. So do not stress on why 56.9. This is coming from the self weight calculation of the Pier cap. So I will apply this and this one now. Okay. Then I will do one fixicity thing. Assign frame releases. So we release the member because we don't want the member to create moments and all, because we only interested in the axial forces. Truss, the basic idea, the basic logic behind the truss is it shows the axial forces. So I will release these things. I will apply, close, display. Okay, so let us check it once. So again, dead load is applied and the these loads are also review. So okay. So we are good to go. Our forces has been applied. Now let's do run analysis. Run now. Okay, this is all structure guns. Then I will show you the output results. Frame, I will see select the dead weight plus structure 5, strength 5, because this is the load combination I've selected for this. Axial force, show values, and I will just click on apply. So this is the result. So let's observe the result. Since it is a bent cap, so the bottom one is giving us tension, so it is good. These are the struts members, so this is giving us the compression. The reds, the negative values are compression, so this is also good. This is the vertical member, which is showing the positive tension force, so this is also good. And similarly here, here, and here above also. So this is fine, and this let's match like whether this output result is matching with our original calculation or not. I have my already pre-calculated value in my report. I will just match whether it is okay or not. So I have opened this. Okay, yeah, this is the same report. So I will just paste the output here. Okay, yeah, this is the output. So our forces and the forces which was present in the report, they are matching. So we are good. Whatever we get again here, this is same here. So this is a good thing that we have get the same results. Now, what if we are like this is done because I have already done this. I was just wanted to show how you model it. But if someone else is doing first time or like for if he doesn't know what would be my stress, so what will he do? So I have one another model which is shown for the inefficiency. So here you will see the difference here. First thing, the vertical ties are in more numbers. The members are also in more numbers. And let's see how the results are given. The loads have been already applied here. Just to save time. Just yeah, let me show you the loads. Yeah, the loads are already predefined here. Let's see the strength 5 loads. Okay, the loads are already predefined. Just we will compare the results. We will do run analysis, run now. Okay, done. We will see the results from SAP. So values, axial force, because we are only interested in axial force. My close. Okay, so this is how it is showing me the results. And let's compare this. Is it good? Is this what we wanted or no? So first of all, as you can see, this member, this is a diagonal strut, but why it is showing a tension force? This is not good. This is not we have expected. Then this member was a vertical tie. It was supposed to show me the tension as this member, this 628, but it is showing me a compression. This is also not a good sign. Then if you look closely between this member and this member, this is a tie, this is a strut. I feel like here at this point, maybe some angle issue is there. Let's see. If we measure the angle that is my angle is greater than 25 or less than. So here you can see the angle is 22.106 degree, which is less than 25. So this is not good. So here, as you can see, this is totally an inefficient model, which one might do, which I have done also when I was doing it, because we don't know what would be the output. So these are the things which we keep in mind, that okay, the angle should be good, the angle should be greater than 25 degree, the diagonal members should show compression only, the vertical members should show tension only. So these are the things uh, which are observed in a good STM. But here these are things coming in, like as you can see, angle issue is there, the forces are not good, mismatching. So this is the example of poor STM, an inefficient model. We will reject this, we will not follow this. So with this, I will conclude my presentation. Thank you all for giving me such time, and I hope you guys have enjoyed it and at least learned like some things from my presentation. Yeah, so thank you all. And